just hit record. Okay.
Okay.
Now you'll be able to save this to either YouTube or Zoom. I prefer you save it on YouTube. Do you follow me on that?
I'm following. Yeah.
And then send the link information to me, and I'll post that link information on OneNote so everybody can get to these recorded lectures. Do you mind doing that for the class? And I'll make it up to you, believe me.
Okay. I can do that.
And I'm doing this because I found this. This is my own personal experience. Students, if they're running the show, they can have these recorded lectures, and they create. The last class I taught, the last couple of classes, they created something called GroupMe. Are you familiar with this, GroupMe? Now, I think you can do this very quickly in GroupMe. You're just I can give you the course roster. And that way, you guys can communicate with yourselves, discuss homework, do what you want, and there's more or less no problem about having the instructor available and present. Now, if you need me for something, just contact me, but I found it worked really well in 2120 last semester and in 3810, and I've done just about every course for the last 5 years. I've had somebody record it and put it online, and they liked Facebook, and now it's GroupMe they're using for conversational stuff. You're all familiar with GroupMe, I assume, right? It's not a foreign thing to most college students. So would you mind doing that, Ben?
Making a GroupMe.
Yeah, do you know how to do that?
I can do that. Yeah, I can look at the list on Canvas, I think, and do it from that.
Well, the problem is I don't have the actual emails for everybody. Hold it, I got a question coming in from a student. All right, I got to email this guy the Zoom link. Hopefully he'll figure this out. All right, got another person. All right, we're up to 7. I got to see if I got any more email. I figured this was going to be this way today. Got a lot of people that are unsure. Is Caleb Flowers in here right now? Yeah, you're there. Okay. And by the way, if you're contacting me, don't use Gmail. Always use your Auburn edu address, because they're blocking Gmail and they're like assigning it to spam or junk. So make sure if you're contacting me, you use your Auburn email your .edu account, auburn.edu. What else? Okay, I'm looking. So far, we have 7 out of 12. What else to do here? All right, and if you're coming in, turn on your cameras and your mics, unless you're, I guess you don't have to turn on your microphones, but it's easier for me to communicate with everybody if you've got mics and cameras on, and I just ask questions about your understanding of things. All right. Do me a favor, Ben. Keep an eye up there. And if anybody else comes in, please, well, hopefully you won't have to admit him, because you said admit everybody, right?
Right. I think it worked where the last person came in and I didn't have to admit him.
Yeah, I saw that. Good. All right. We'll just hope for the best. Now, what I want to do is go ahead and start this course and explain a few things. My name is Mike Baginski, and you probably figured that out. I've taught this course many, many times. This is the first time I've ever done a Zoom delivery. And I want to tell you, when I've taught other courses where we've had a camera and I was doing a remote delivery, the person could ask a question real time like this, but I had an entire board I could write on, and they would just have a high definition recording cast. That's the way I'm used to doing things. I like the board. Now I have to resort to a tablet and write everything here. I'll go slow and I'll try to show you everything. I do not like PowerPoints, and I don't like anything that's just predefined slides unless it's absolutely necessary. So what I'm going to do now is switch to this yellow tablet, and I have a note set here, but I'm going to go through this. And I want to tell you what we're going to start with is transmission lines. Now, you've all had circuits, correct? Right? And if you have had circuits, if you can turn on your cameras, please, and turn on your mics. If you had circuits, you remember there's three essential components, the lumped element components that we use as elements. One is an inductor. These are passive elements. The other is a resistor, and the third is a capacitor, correct?
Yes, sir.
And you're familiar with those in both the time domain, where like the current through a capacitor was C dV dt was equal to the current through a capacitor, and L di dt was the actual voltage across an inductor. That's the differential equation, actual identification of the voltage current relationships in these components. But in continuous time, if we assume a continuous frequency, say a cosine of omega t is the input frequency, then you know that instead of working with differential equations, you use the, couldn't hear you?
Yes.
Did you have a question?
No.
Okay, all right.
Sorry.
That's fine. No, it's all right. You can interrupt me. But anyway, if you've had that, then you remember if you go to continuous time, instead of, or I should say, continuous frequency, a cosine of omega naught t plus some phase angle, then you represented the impedance of the inductor as just j omega L, and the impedance of a capacitor is 1 over j omega c. Do y'all remember that?
Yes, sir.
Okay. With that, now we're going to go to transmission lines, and I'm going to have to cast the screen. If something's amiss and you don't see something or can't hear or whatever, let me know. This is the first. All right, I got somebody else that needs a little information. I received it. I received the email you sent. I'm just wondering if we will not have any meetings online. This never goes well. Give me 1 second. I gotta share this. I think some of these people have never had a class online. Something else I'll tell everybody. When you're sending the email, don't send it to my .outlook account. I don't know why Auburn does this, but I have a BAGINME at outlook.com account that somehow it defaults to when you're in Canvas. And I have a BAGINME at auburn.edu account. Now, the Outlook account doesn't always get to me. So I'm telling you that in fairness. Does everybody understand that, class? All right. I'm going to have to just start this, and I'm going to go ahead and share the screen. I'll do the best I can, but I'm trying to keep an eye over here if people send me messages that they don't know how to get in or anything like that. So now you can see the MATLAB, Octave, Python statement again, right? Can you all see it or not? Oh, it's not sharing yet? Hold on. Is it sharing now?
Yes, sir.
Okay. So the lecture starts this way. We're going to be talking about transmission lines. And the first thing I'm going to do is identify what a transmission line is. I'll try to write better. It's nothing more than two conductors separated by a constant distance. For instance, if you have two wires that are separated by a constant distance d, and these are copper wires, so you could put copper wire. These are good conductors, and that would be a transmission line if one thing was true. If the length of this line was greater than a tenth of a wavelength. Now, I assume everybody understands what a wavelength is. Is that right? Let me try to get you all here. I'm trying to get a view of everybody, and Zoom does not automatically give me that when I'm sharing the screen. I have to refashion the screen. But if you can turn on your cameras, please do, and your mics. But so if you have an extension cord, that would theoretically be it would be a transmission line. Sorry about this. Or can you name another transmission line? Think about it. I just want two conductors separated by a constant distance. And you know what a conductor is, right? Copper is a good conductor. Think about it. Think about what comes into your home. How do you get your TV, most of you? There's one thing that brings it into your house. What is it? A coaxial cable, right? Does everybody know what a coaxial cable is? Yes or no? I'm looking at everybody. Can you hear me?
Yes, sir.
You can hear me. Do you know what a coaxial cable is, everybody? It's what, the cable that comes in for Spectrum or Cox or any of the internet service providers, right? It's a coaxial cable. It has an outer layer of, it's really a woven foil, and then it's an inner central core, a solid piece of copper, and it's got an insulator, correct, class? It's cylindrical. Those are two conductors. There's an inner core and an outer core, and they have an insulator between them. Now, what that allows to happen is this. If you have a coax cable like this, and I'm going to take the cross-sectional view. If you have a coax cable as such, then there's an electric field that's developed that's radially distributed, radially outward, and I'm just showing you E as that. And there's a voltage difference between the inner and outer. And when you have a coax cable or twin conductor lines, and I'll go with the twin conductor lines, either one's true, then what happens is you're going to have a plus to minus voltage difference, and you'll have current flow this way, and the current directly below that at the lower conductor will be in an opposite direction. Now, you're familiar with like an extension cord, the way it behaves, that it's a differential mode of operation. Current goes down one way, back the other. Same magnitude, opposite direction. Do y'all follow me on that, class?
Yes, sir.
Yes.
Okay. And by the same token, you would have electromagnetic energy that would propagate in a certain direction with a certain velocity. Now, generally speaking, that what they show you is something like this for a voltage waveform, and they'll say it's propagating this way. I'll spend more time discussing this in a bit, but I'm just trying to get you a feel for this. You all follow me? If you have two twin conductors, they can deliver information at basically the speed of light because the waves propagate back and forth on this conducting medium, and they move at the speed of light. Do you follow me? Right? It's different than open air communications where you have electromagnetic energy and it just radiates in every direction, but it's not focused or conducted in a certain one. So what a transmission line does, it focuses all the electromagnetic energy on these twin conductor pairs or coaxial cables, and it goes down, it moves in a direction that's that's really along the conductor's length. Both the electric field and magnetic field are perpendicular to the direction of propagation. Y'all follow me on that one? You know, you got something called the motion that you can hit. You can hit a thumbs up or thumbs down somewhere on there. Can y'all find that? Just for kicks, see if you can find it. You got Okay. That tells me you got it. Do y'all see a thumbs up or probably a thumbs down? I got 3 I'm looking at. Can you all see these people too? Or am I the only one seeing them? Can you all see each other, class?
Yes, sir.
See if you can find that thumbs up. That tells me, even if you don't want to turn on your mic, that you know what's going on. All right. Well, I'm glad most of you got that. And so this will get better as we go on, by the way. So now what I'm going to do is, based on your knowledge of circuits, I'm going to say that we can take any twin conductor line and we can represent it in a differential form by certain components. So if I have, I mean, just think about it. If you have a piece of copper wire like this, right? You know, if you have copper wire and currents flowing in it, well, even though it's small, there's some resistance. Do you agree with that?
Yes, sir.
And if you have current in a wire, there's a magnetic field that's set up automatically, isn't there? You can't avoid it. And that magnetic field causes magnetic energy in the environment around there. And the minute you have magnetic energy, you have an effective inductor. So what we do is, when we're talking about current flowing down a copper line over a differential distance, we say there's a certain amount of inductance, L prime, and a certain amount of resistance, R prime, and these are per unit meter terms. And they just have to, what you end up doing is this: you're going to say that if I have a twin conductor line like this, and there's a separation D, and the length of this twin conductor line right here is delta Z, so it's very small. There's a certain amount of inductance and resistance associated with the current flowing down and then returning here. But there's something else. If you have 2 wires separated and you have a voltage difference, you also have electrostatic energy. Do you all agree that if you have a voltage difference between any 2 points, there's an electric field that exists between those 2 points? And if you have an electric field in a region of space, you have electrostatic energy. Do you all remember this from physics? Everybody? All right. Now, if you have electrostatic energy, you have capacitance. Do you agree with me? But it's between the lines. So what they do is this: they're going to say there's a certain amount of capacitance between the lines per meter. And there's one other thing. Even though it's going to be an extremely high resistance or extremely low conductance, if you have a voltage difference even between 2 points in air, there's still a certain amount of leakage current that will flow. Does everybody follow me on that? The only time it will not flow is in a perfect vacuum. But if you have any type of material, and here it's air, between 2 points of space, and there's a voltage difference, then current will flow. It's very small, but there's still a theoretical measurable amount of current that's flowing there. And they represent that not by resistance, but by a conductance. Now, conductance is usually something you don't think about, but conductance is really 1 over resistance. But it's not this resistance. This resistance here that I'm showing you, and I hope you can see it, is associated with the actual resistance of the copper wire down and back per unit meter. And this is the resistance of the insulation per meter. So over a given length, and I'll call this delta Z, we have a certain amount of differential inductance, differential resistance, and capacitance and conductance. Now, there's a voltage that's going to be between here, and I'll call it V of Z. And there's a current that's flowing here, I of Z. You all follow me on that? If you have 2 wires, this is theoretical now, you're going to have a voltage difference if you want it, and that voltage difference will cause current to flow. Does that make sense to everybody? Can you all see this okay? All right. Now, if there's a current flowing here, there's going to be a voltage drop between these 2 points, or between here and here. And the voltage drop will be caused by the losses in the inductor in the resistor, correct?
Can you move it down a little bit, sir?
Oh yeah, I'm sorry. I'm trying to watch that and watch your expressions too, to see if you're getting it. I mean, you follow me on this. If you have current flowing down a line, you're going to have a voltage drop between these 2 points, right? Because the current would cause a voltage drop on the resistance, which would be I times R. and a voltage drop in the inductor. And we're going to go and move right into we're going to assume a continuous frequency of excitation. So instead of putting L there, I'll put J omega L. That would be the impedance of the inductor, correct? Y'all see that?
Yes, sir.
Ben, can you see this okay?
I can
put
see
it
that.
up there?
Yeah.
Okay. There's also going to be, if you think about that, that's going to be a voltage drop. So if I say that the drop, it would be minus dV dz here would be equal to I, that would be the current, times R prime plus J omega L prime. Do you agree with that? Remember, it's a voltage drop, so it's the change in voltage. dz, I didn't put a small dz here, I used a delta z, but it's per whatever this is, differential distance. Do you agree with me? Can y'all see this? Okay.
Yes, sir.
Stay with me now. Trying to get a little better pen. All right, if that's the case, then there's also going to be some current. Now, follow me on this. There's some current that's actually going to bleed off this way. And I'm going to call that a delta I. Do you agree that because there's a voltage difference, current will flow through the capacitor and it will flow through the conductance G? Do you agree with me? Are you with me, class? It will. And if that's the case, I'm also going to have a minus di dz. This is the amount of current that's going to be shunted off. Most of the current is going to continue flowing in this direction, but some is shunted off through the capacitor and its conductance here. And that would be equal to, well, what's the current through a capacitor? Isn't I in a capacitor equal to C times dV dt? Or I is equal to what? J omega C times V, isn't it? Y'all remember this? You could say that if you looked at the impedance of a capacitor, it's 1 over J omega C, correct? And impedance is a ratio of voltage to current. So if you wanted the current, it would be J omega C times the voltage. And the current through this is really going to be the voltage times the conductance. Because remember, how many are familiar with the symbol G for conductance? Thumbs up or thumbs down? One. You're not. You remember when you had Dave Ehrman's circuit class, one of the things he taught you was there was a symbol for conductance. It was 1 over resistance. Do you remember that at all? Some of you might. It's not used very often in engineering, but here it's useful because now I can say that the rate of change of the current with respect to Z would be equal to the voltage V times, and this would be G prime plus J omega C prime. Now these are two equations that are symmetric. They look about the same, except there's a slightly different symbol. One has current, the other has voltage. Y'all follow me on that? But we have both voltage and current in these equations. Now, this is important what I'm about to say. Whenever we do transmission line analysis, we assume that the resistance per unit meter, R prime, the inductance per unit meter, L prime, the conductance per unit meter, G prime, and the capacitance per meter, C prime, do not vary versus the length of the line. So if you have a piece of coaxial cable, the amount of inductance per unit meter is the same at the beginning of the line as at the end. There's no change in the parameters. And what that implies is the cross-sectional area of the transmission line is the same, it never changes. For instance, if you have two wires and they start flaring out like this and the separation distance gets larger and larger, are you with me on this? Then you would have a different value for capacitance and inductance per unit meter, and as well as resistance and conductance. So that this method would not apply, but almost all transmission lines maintain a constant cross section. And when I use the terms coaxial cable, everybody needs to be familiar with that. Are you with me on that one, class?
Sure.
And when I use twin conductor, like an extension cord, you need to have a picture in your mind of two wires that are separated by a constant distance. And I think you all have that, correct? Okay. So now we'll go on. So with these two equations that I'm going to recreate, you don't need to write this down. In fact, I'm just going to create them again. If I have minus dV dz is equal to I times R prime plus J omega L prime, and minus di dz is equal to V times G prime plus J omega C prime. I'm going to use these two equations to develop one single equation. And this is something that you see over and over again with vector mathematics as well as these are scalar mathematical equations. It's to develop something called the wave equation. Do you remember in physics you learned about the term wave equation or Helmholtz equation? Remember that? Does anybody remember do you remember how to get propagation? It was from the wave equation. On a string, for instance, you had a tight string and you wrote a differential equation for displacement in the vertical direction versus tension. Remember doing any of this? I'm not seeing a whole lot of head shaking. Okay, well, that doesn't matter. This is going to be used. You're going to do this over and over again. Engineers live in this world of differential equations. You have to love them because that's what we end up writing. Everything in life, by the way, just for the record. Everything in the universe we know is explainable mathematically by really integral differential equations. We can write expressions for the behavior of the universe, of lightning, anything like that in terms of integral differential equations. So it's combinations of integrals and differential equations. And a lot of times it's not, I mean, the coordinates are both spatial as well as temporal. So there's all sorts of equations and you're familiar with some of them. But for this is a nice one. It only has, the only spatial variable is z. So we're going to take a derivative, another derivative of the first one. So I have minus the second derivative of v with respect to z squared equal to r prime plus j omega L prime times di dz. You can see here, the only thing I've done is take another derivative of the equation. And I'll even label that as 1 and label that as 2. Do you all agree with that? Remember, r and L do not change with distance, so I don't have to take a derivative of the r and the L also. That's like a scalar. Are you all with me on that?
Yes.
All right. Now, I want to get one equation with only one unknown, so you can see that I can replace di dz right here with this di dz, correct? Take a careful look. You all see that?
Yes, sir.
Now I'm going to do that. And when I do that, I get this. I have minus the second derivative of v with respect to z squared is equal to r prime plus j omega L prime. And then di dz would be what? It would be minus this v times g prime plus j omega c prime times v. And I didn't say this, I mean, I didn't state this down in writing, but both r prime, L prime, C prime, and G prime are all per meter. Quantity. So it's resistance per meter, capacitance per meter, inductance per meter, and conductance per meter of the wires. You follow me? Okay. Now, you're looking at this and you're saying this is getting a little bit, it looks a little bit, I don't know, awkward to work with. So what we do is create a new term. Do you see this right here? What I've just put in brackets? We'll refer to that as gamma squared. So gamma squared will be equal to r prime plus j omega L prime and g prime plus j omega c prime. But we really don't like to talk about gamma squared. What we want to do is talk about gamma. Gamma is called the propagation constant. So gamma is the propagation constant, and it is equal to alpha plus j beta, but it's also equal to the square root of r prime plus j omega L prime times g prime plus j omega c prime. Now, follow me on this. You've had circuits, you're familiar with resistors, inductors, and capacitors, right? I'm really, I look to you as I would my class. When I don't see, when kids are like, what are you talking about? Then I have to go back and try to figure out there's an uncertainty, what they don't understand. But you all know what capacitors, inductors, and resistors are, right? You got to know that much, or else you shouldn't be here. All right, well, we use the per unit length values of these to come up with something where we have a single differential equation expressed in terms of the values of R, G, L, and C. And we've equated this to a real and imaginary term. Now, this value alpha is called, this is the attenuation. And you can put down loss. So alpha is associated with attenuation and loss. Beta is the wave number. Attenuation is always given in Napiers per meter, and beta is given in radians per meter. Now, I'm going to explain something as easily as I can. When you have a resistor and or a conductance in a line, and current flows through it, do you agree energy is going to, or power is going to be changed into heat? Do you agree with me that electrical energy would cause heat? Are you with me? The minute you have resistance or conductance and there's a voltage applied, you have what's called loss. And that means the sum of the signal isn't going to be available. When it's going down the line, the signal is going to attenuate or decrease. And we'll see that in the equation. The wave number has to do with the frequency. Radians per meter. Radian is a term that has to do with an angular change, right? So if you have a certain number of, you have what? You have 2 pi radians in 360 degrees, correct, class? There's 2 pi radians in a wavelength, isn't there? There's a full 360 degrees in a wavelength. So when we talk about radians or wave number, the larger that quantity is, the higher the frequency. And I'll spend more time on that in a bit. When we talk about attenuation, the larger that constant is, the more loss there is per meter. Make sense? I'm going to give you the exact equation that specifies voltage and current. But for now, I want you to appreciate what these things actually signify or what they mean. Now, when I have this equation, I'm going to go back to the one up here. And you can see the minus signs cancel, don't they? They appear on both sides, correct?
Sure.
Now what I'm going to do is this. I'm going to take this term right here and replace it by gamma squared. And then I'm going to get an equation set equal to 0. So I'll take this term to this side. And what it looks like is this. I'll have the second derivative, v with respect to z squared, minus gamma squared, v is equal to 0. And by the way, v is indicative of the voltage. Y'all follow me what I've done? Now I could solve this. I could go through the solution using a Laplace transform if I want, or I could do use an integration factor, but I'm going to tell you what the solution to this is. Just straightforward. V as a function of z, and this is a phasor V. Usually in circuits, Dave Irwin didn't really force this, but you know, when we talk about phasors, they're magnitude at an angle. Like if you had a voltage of 10 volts times cosine of 377t plus, say, pi over 4 rate, or make it, say, 45 degrees. So you had 10 cosine of 377t plus 45 degrees, and you were putting that in terms of a source on a circuit, you would not represent it that way. You would represent it at 10 at 45 degrees. The cosine of omega t term is suppressed. Do you remember this, class? Okay. The term that's, when you're suppressing that cosine of omega t plus phase angle, it's called the phasor domain. And there's usually a squiggly line over the top of the voltage or current to identify that. Now, that's not true in Irwin's class. He didn't force that. Y'all had Dave Irwin, didn't you, for circuits? Or if you didn't have Irwin, I'm not sure who you had, but Irwin, in my opinion, was the best circuits teacher. I guess you have a couple, you have what? There's a couple of lectures that are now online that are doing it too. Linda, is it DeVore or something like that? And there's also Daniel Geiger, I think, teaches it too. But there's other people teaching it now. Anyway, Irwin was probably the best. And so the solution will be this. It'll be some V0 plus e to the minus gamma z plus V0 minus e to the gamma z. Now I'm going to explain something to you. This is a phasor representation right here. And this indicates a wave going in the plus z direction. This indicates a wave in the minus z direction. Remember, this is phasor, right? It's constant frequency, suppressed cosine of omega t, right? By the way, can you all follow me on this? There's two terms. In general, there's a forward propagating term given by this. V0 plus is the magnitude of it. And there's a reverse, or a wave traveling in the negative direction. Now, I'm going to tell you to notice this. There's a minus gamma here, and there's a plus gamma z there. But V0 itself has a minus sign to identify it's going in the negative direction. It's the coefficient of that wave. Do you all follow me on this?
Sure.
Yes.
Now, I don't know if you remember this, and so I spend just a second doing this with everybody. Do you remember when you had, if you had what, 10 times, or a 10 at an angle of, say, 30 degrees as a voltage V in the phasor domain? If you wanted to get the time domain expression to that, you would say V in the time domain, and I'm going back to circuits for a reason, because if you understand circuits, I can use it to bring you into an understanding of this easily, but if you don't, it's hard. You're familiar with this form, right? For voltage, 10 at an angle of 30 degrees, right? If you want it in the time domain, the way you actually get it was take the real part of V phasor times e to the j omega t. That's the mathematical linkage between the phasor and the time domain. I don't know if you remember that, but that's the mathematics. Here's where I have to make sure you understand this. This becomes essential. When we talk about e to the j omega t, using Euler's identity, that becomes cosine of omega t plus j times the sine of omega t. Are you familiar with that? That is Euler's identity. Now, if we take this expression and we look at the real part of it, the real part would be the part that has the cosine of omega t, not the j, correct, class?
Sure.
I'm going to go ahead and do that with this equation. If I put this equation in here, I'm going to have to turn the page. Forgive me, but turn the page on this one. And now if I take a look at this and I go ahead and I'm just going to use the positive traveling wave to do this. So I'm just going to say we have V0 plus e to the minus gamma z is my voltage. And that would be equal to V0 plus e to the minus alpha z times e to the minus j beta z. And this is still in the phasor form, right? This is still a phasor voltage. Do y'all follow me on that, class? Now I'm going to get it in the time domain. So to get it in the time domain, V here would be of ZT, would be the real part of this V0 plus e to the minus alpha z times e to the minus j beta z. But you have to multiply times e to the j omega t. Y'all remember doing that or not in circuits? A lot of people don't. Remember, if you had a phasor, if you had 10 cosine of 30 degrees, and you want it in the time domain, what you really did is multiply 10 cosine of, 10 at an angle of 30 degrees by e to the j omega t, and then you took the real part of that. I'm going to show you that right here. So if I have this equation right here, that's really equal to what? The V0 is a constant. I can take that out in front, right? E to the minus alpha z, well, that's real. There's no imaginary part of it, right? If I had e to the minus 10z, regardless of what z is, it's still a real value. Do you follow me? There's no j, correct? So I can take that out in front as well. Now, I need the real value of this? Well, it leaves me these two things, and that would be e to the what? J omega t minus beta z. And the only thing I've done is what? Added the exponentials of e, right? I have e to the j omega t and e to the minus j beta z, correct? Y'all see it? Now,
Yes.
when I take the real part of that, well, if I expand this, I get a cosine of omega t minus beta z plus j sine of omega t minus beta z, right? Correct? In other words, you would have a cosine with the argument being omega t minus beta z and j sine of omega. The only thing they care about is cosine. So that means my v of z comma t would be equal to v0 plus e to the minus alpha z times cosine of omega t minus beta z. Are you with me? That's the time-space equation that describes a propagating wave going in the positive z direction. This wave is moving in the plus z direction. And you can always tell the way it's moving because if you look at the coefficient of the spatial vector here, or the spatial quantity, you see how it's z? There's a minus beta. Minus beta means it's moving in the plus z direction. If it was plus beta z, it would be moving in the minus z direction. Now I'll add the other term. This is a wave moving in the plus z direction. And if you had a wave moving in the negative direction, it would be v0 minus times e to the plus gamma z. And it would be cosine of omega t plus beta z. And this wave is moving in the minus z direction. And that is a description of the voltage that's propagating on a transmission line. Okay? Can you all follow that development? It started with the differential equation, came to the general solution, and now from the phasor domain, I brought it into the actual time domain. This right here is a temporal description of it. We don't generally use this type of description because it's clumsy to work with. If you look at this right here, right? What do you notice? Well, there's a lot of terms. In the phasor equation just had what? It had this, just v0 plus times e to the minus gamma z, and gamma included alpha and j beta. So it was a more compressed way and compact way of expressing this. But this is the time domain equation. Now, the reason I'm saying this, and I'm showing this to you, is the time domain equation is something that is observable. If we take a voltmeter and we stick it across that transmission line and we know where we are in Z, we can measure this waveform. We could measure the voltage. Do you follow me? We can't measure a phasor voltage. I mean, you can get into theoretical arguments about this, but phasors by their nature mean that they're non-observable. They have that J. You follow me? J is the square root of -1. It's a non-observable quantity in the physical world. I want to tell you one other thing. If we went down the track and instead of went for voltage, if we took those two differential equations we started with, don't turn there, I'm just going to show you this. If we started with these two differential equations right here, and I took another derivative in I here, I would get a second derivative I with respect to Z squared equal to, then it would be a first derivative of V with respect to Z. Can you all follow me on that? I'm sorry. Yell at me if you can't see what I'm talking about. You remember these equations that we started with?
Sure. Yeah.
Well, we took a derivative of this one, another derivative, in order to get the equations that I used. If we took a derivative of this one, we'd have second derivative of I with respect to Z squared. And then we have first derivative of V. So we take this expression for V and stick it in here, and we get an identical expression only in I, not in V. And the solution would be this, and I'm going to put this down. The solution would be, if we did that, we're not going to do it because it's redundant. You would get I of ZT equal to I0 plus times e to the minus alpha Z times cosine of omega t minus beta Z. And that would be plus I0 minus e to the gamma Z cosine of omega t plus beta Z. it would be identical except for the V would be replaced with I. And I, of course, signifies current. It's in amps. V symbolizes voltage, and it's in volts. All right. All right, next. After that, we got to talk about some basic concepts. The first one I like to talk about is wavelength. Lambda is a symbol for wavelength, isn't it? Do you remember that? Isn't that consistent with physics? Well, wavelength means what? If we took a look and froze time, and this was voltage, and this is time, or better yet, this is space, this is Z. Say we freeze time and we take a look at the voltage at a point in time, and it looks like this on a transmission line. Well, the wavelength is always going to be the distance over which the wave starts repeating itself. So it's the distance where you go from 0 to 360 degrees or 2 pi radian change. Correct, class? You're familiar with wavelength, right? And the way we get, I mean, that's the wavelength itself. We're going to get wavelength and some of the other quantities from these equations. There's another thing we talk about that, remember here, I'm freezing time. So T is assumed to be like 0, or actually not 0, but just say a constant C. And if we took this and we froze space and we let Z equal 0 and take a look at a plot versus time of, say, the voltage. If we let Z equal 0 and then we take a look at time. If Z equals 0, then this is just V0 plus times cosine of omega t, right? And we can forget about this one. But if you look at that, if you freeze time, this is wavelength. I'm showing you here, and I'll give you the equation for it in a second. Now we're talking to look at something called the period of a wave, or the symbol is cap t. And if you freeze space, say Z equals 0, and this is time, then what you'd end up getting is actually this. I'm trying to draw a cosine waveform there. It's not coming out very well, but the period would be t. You're familiar with that as well, correct, class? One other thing I'm going to talk about, and I'll get to the equation relationships here. When you take a look at velocity for a second, we know if this wave is propagating to the right, a little bit later, what you would see is this. You'd see the wave like this, right? It would start moving where the actual crest of the wave is moving in that direction. Just think of waves on the ocean, right? The crest is what you look at to try to estimate the velocity of a wave, right? It's at a constant phase point, if you will. Joel, follow me on that? All right, now if we want to calculate the actual velocity of a wave, we go to the equation, and I'm going to go to this equation right here. Come on, there you go. We take this equation, and what I'm going to do is hold the phase constant, but I'm going to get a new sheet of paper. I will get better at this as time goes by. But if we take a look at voltage, V of ZT, and for this one, I'm just going to have a positive traveling wave and say it's equal to V0 plus times e to the minus alpha Z times cosine of omega t minus beta Z. And this is, again, a positive traveling wave, right? How many are familiar with that equation? At least it's not something that you've never seen before. Can y'all just give me an indication? You haven't seen it? How many have seen this, something like this in physics or in your in circuits? You've certainly seen something like that, didn't you? Right.
See something similar, but not exactly same, like lots of different expressions.
Yeah, there's different symbols for this. Usually in physics is the first time you see this thing over and over again describing, and it has to do with like displacement on a string, a taut string, and they get the velocity on a string. And then there's other places in physics you get things for the equation, sound waves propagating, it's compression, refraction, things like that. But this is a basic equation for voltage on a transmission line. And if you look here, the argument of the cosine, that's an angle, isn't it? That's really phi. Cosine is always a cosine of an angle, either in radians or in degrees, correct, class? Now, if you take a look at this and you want the rate of change of that phase to be 0, so I have phi is equal to omega t minus beta z. If you're talking about phase velocity or the crest of a wave, right, the top of a wave, that's a phase point that's constant. So if you take the derivative of the phase and set it equal to 0, if this is phase, if I take the derivative phase and I set it equal to 0, what I have is a definition of the point, either at the peak of the wave or at some point on the wave that you're tracking. Think of a surfer on the top of a wave. You're tracking how fast that surfer is moving at a constant phase point on the wave. Well, a derivative of omega t with respect to t is omega, and a derivative of beta z, beta is a constant, by the way, this is constant frequency, would be minus beta times dz dt. And when you think of dz dt or dx dt or dy dt in physics, what do you always think about? What is dx dt in physics? It just should jump right in your mind. Anybody?
The velocity or speed.
It's a velocity, and that's exactly what this is. The ZDT is the velocity of the crest of the wave or any part of the wave, how fast it's moving. So if you rearrange this, you could put what? Omega divided by beta would be equal to the actual velocity. But this velocity is not the velocity of energy necessarily. It's called the phase velocity. So write down phase velocity. The phase velocity is omega over beta, and that will always be true. It doesn't matter if it's lossy or not, it will always be true. And you've heard that. Now, if we talk about this basic equation here, and we wanted to figure out the actual period or the wavelength, well, look at this for a second, cosine of omega t, and forget about this. If we take cosine of omega t minus beta z, all right, and just say that that's equal to some theoretical voltage. In other words, the magnitude of that voltage is 1, isn't it? The coefficient of the cosine. All right, now I'm going to go through a thought experiment with you. Let's let t be equal to 0. So we're going to freeze time. And now I have v is just equal to cosine of minus beta z, right? With me? I let t be 0. That's still something you can plot versus versus z. But what do you know about a cosine waveform? Isn't it called an even function, and cosine of x is equal to cosine of minus x, isn't it? Do you remember that it's called an even function, right? And if it's an even function, I can get rid of this. Now, if I plotted this versus z, if I plot voltage versus z, I'd get something that looks like this. Do you agree with me? You plot cosine of anything, right? It's going to have a sinus or cosinusoidal variation. Do you agree with me? The wavelength you told me before was, you agreed with me that it was this distance was lambda, right? Spatially speaking, right?
Excuse me, could you scoot it down just a little
Oh,
bit?
I'm sorry. Thank you. Thank you. So this would be a wavelength from crest to crest, correct? You agree with me?
Yes, sir.
I'm making sure you can see this, and I'm trying to look at faces because I can tell with faces much easier than blank screens or black screen. So from here to here is a wavelength. Well, how far is that? This point is 0, isn't it? It's where beta z equals 0, right? What's this point? Beta z equals 2 pi, isn't it? It went exactly 2 pi radian change. Do you agree with me? So when I say the argument here of beta z is 2 pi, that's a wavelength. So I can say that beta times a wavelength is 2 pi, or that a wavelength is 2 pi over beta. And that is the definition of a wavelength. And wavelengths are in meters or centimeters or millimeters or micrometers, but their unit is distance. Do you follow me on this, class? Okay, that's a wavelength. Now, so I've got phase velocity and wavelength. These are both important. What about period t? how do I get period T? Think about it. Go back to this equation right here. All right. We froze time for the last one. Here, we're going to freeze distance. You follow me? We're going to let Z be 0. So if Z is 0, I mean, right here, then it's just cosine of omega t, correct, class? Y'all, when I say freeze, I mean, you set Z equal to 0, it's no longer part of the equation, right? If Z is 0, then this equation right here just becomes cosine of omega t, correct? Now we can graph it. And so if we let Z equal 0, and we go ahead and we graph cosine of omega t, it does this.
Can you move it down?
Yeah, thank you. And this is time, right? And this, from here to here, crest to crest, would be t, right? You all agree with that? All right, well, what is that? Well, this was cosine of 0 at this point, right? What's this point? This would be omega t equal 2 pi, correct? Y'all follow? If it started at 0, 2 pi radians later, it's gone through 360 degrees. And that means omega times capital T, the period, would be 2 pi. And the period would be 2 pi over omega. That's fundamental, but I'm going to make it easier for you. From circuits, what is omega in terms of frequency?
2 pi f.
That's right. So you can say period is really equal to 2 pi over 2 pi f, or it's really 1 over the frequency. Period is 1 over the frequency. Everybody follow me on that? I'm going to remember that, or at least it's jogging things, right? Remember, it's, you got to, this is something you're going to have to use all the time, by the way. Now, next, what we're going to do with these equations is we're going to get into something, well, we're going to do quite a few things, actually. The next thing we're going to do is talk about something called the characteristic impedance. So write this down. I have to do this before I can do problems. I got to take you through what they're talking about before I can apply it to problems. But characteristic impedance is really a ratio of voltage to current. So if you think about the differential equations, we had dV dz minus that equal to I times R prime plus J omega L prime, correct? And we had an equation for V and I. Now, what I'm going to do in order to keep it simple is I'm only going to take a look at waves that are propagating in the positive Z direction for now. So if I do that, I can say that V is equal to V0 plus e to the minus gamma Z, right? And I can say that I is equal to I0 plus e to the minus gamma Z. You realize I'm just talking about the positive traveling component of both voltage and current. Are you with me? All right, now with that, if I take a derivative of V with respect to Z, if I take dV dZ, I get V0 plus and then minus gamma times e to the minus gamma Z, don't I? Right? A derivative with respect to Z would bring out the gamma, but it would bring out a minus sign as well. Do you all see that, class?
Mm-hmm.
Now, take a look at this. Now I'm going to replace this minus dV dZ, or make this what? This equation here would become V naught plus gamma times e to the minus gamma Z was equal to, well, I is this, so I'm going to put it in there, I0 plus times e to the minus gamma Z, and then it's times R prime plus J omega L prime. Do y'all agree with that? I've condensed things. All right, I want you to take a careful look at this. What do you see that cancels on either side? Anybody? Tyler, what can we cancel?
You do the minus gamma z.
Yeah, let's get rid of those first off, right? And now this is important. This is the characteristic impedance. The symbol for characteristic impedance is Z naught plus, by the way. And now you can say that Z naught, or we can take the ratio of V0 plus to I0 plus. Remember, impedance is always a ratio of voltage to current, isn't it? Impedance is always the voltage to current relationship of a component. For a resistor, resistor is the impedance, correct? And this is given the symbol Z naught plus, and take a look what it's equal to. Well, V0 over I0 would be equal to what? R prime plus J omega L prime over gamma, correct, class? Make sure you see this. You with me? Now, this right here, gamma, that's just R prime plus J omega L prime over gamma. Gamma is equal to the square root. Let me keep going down here. Z naught plus would be equal to R prime plus J omega L prime. And gamma is the square root of R prime plus J omega L prime times G prime plus J omega C prime, right? Remember from before, you can look back at it. I'm just restating the fact that what gamma is defined as, right? Y'all remember this, class? You can look back in your notes, it's there. All right, y'all see how that R prime plus J omega L prime cancels. This is to the 1/2 power, this is to the first power. So now we can say that Z0 plus is equal to really the square root of R prime plus J omega L prime over G prime plus J omega C prime. Could you all see that, class? That's a little messy, but it's R prime plus J omega L prime over G prime plus J omega C prime. And that's called the characteristic impedance. And it's a ratio of voltage to current in the positive direction. So really this Z0 plus is simply V0 plus over I0 plus. Now I want to make a comment. You know, on your cable that comes to your house, have you noticed the term expression 75 ohms anywhere on it? Anybody? No? 75 ohms is called the characteristic impedance of that line. There's 50 ohm coaxial cable, 50 ohms. But the way they get this is, here, I'll show you how they get it. For most transmission lines, they're very low loss. So for a lossless transmission line, they assume that R prime is equal to G prime is equal to 0. So they assume there's no real resistance to worry about, and it's a perfect insulator. You follow me? Everything's perfect. So now what they find out is their Z0 plus is equal to the square root of J omega L prime over J omega C prime, or it's really equal to the square root of L prime over C prime. And L prime is the per meter inductance and C prime is the per meter capacitance. The J omegas cancel out. And that's what you get when you see like 75 ohm cable, 50 ohm cable. It's a ratio of the square root of inductance to capacitance per unit meter. And it will be given in ohms, by the way. That's interesting. This is given in ohms, but there is no loss. So it's a bit confusing. You've heard 75 ohm or 50 ohm cable, haven't you? Or 300 ohm twin line. If you have an antenna that's one of those T antennas on the back of your stereos or anything like that, it'll say 300 ohm line. That's the ratio of inductance, square root over inductance to capacitance per meter. And that's something to keep in mind. It has nothing to do with the loss. All right, y'all with me on this one? Okay. And now something to be said. Since Z naught plus is a ratio of V0 plus to I0 plus, I want to show you this, that Z0 minus is a ratio to V0 minus over I0 minus, and it's equal to minus Z0 plus. So this is going to be important in a second. With me? I can prove that. I'm a little shy on time. I've got 9:13 right now, but y'all with me so far? All right, hang in there. It's not going to be that bad. So we've done phase velocity. We've done that. Now the next thing I'm going to do is talk about power moving down a line. Y'all know that anytime you have any kind of confined electromagnetic energy propagating, like in a cable or in a twin pair, you have really energy moving or power, don't you? I mean, it's inevitable. You can't help but see that. Well, you remember back in the day when you had circuits, power, the average power, was equal to what? It was 1/2 the real part of V times I conjugated. Y'all remember that? How many do from Irwin's class? With a resistor was what? It was V times I, right? But if you had complex components, if you had inductors, capacitors, it was V times I conjugate. And that's the power that's actually going to be propagating down the line. Now remember, we have an equation for voltage and an equation for current in the line. But the power that's propagating, not being dissipated, but propagating, is 1/2 the real part of V times I conjugate. So if you take a look at this, and I want you to watch this, I tend to focus on try to make things simple. I'm going to be talking about a wave just propagating the plus Z direction. We're going to take a look at the power here. This is power. So here we know that V, if we just have a positive traveling wave, would be V0 plus e to the minus gamma Z times e to the minus J beta Z. Are you with me? I broke up gamma into alpha plus J beta. I have the attenuation and I have the actual wave number broken out separately. With me? Remember, gamma is equal to alpha plus J beta. And here I broke out those components for a reason. That's the voltage. The actual current would be equal to, and here's where I want you to pay attention. Remember, characteristic impedance is defined as voltage over current. So if I wanted current I0 plus, I could say it's V0 plus divided by Z0. So I can take it simply V0 plus over Z0 plus times e to the minus alpha Z times e to the minus J beta Z. Are you with me? I think I'm over, but are you with me so far? Give me a minute or two, because this is the first day of class and it's awkward. And Ben, can you tell me how many people we have looking on right now?
Looks like 9, including you, I think.
9 total?
9 total.
All right, so you have 8 students. We have 12 people enrolled. That means we're short 4. I've got to make a note of that, and I'm going to try to contact everybody. All right, let me finish this thought if you don't mind. And I'm sorry about the rough start to the class, but nobody wanted remote delivery. And I can't do my remote delivery in an area where they have a high definition video camera that they can stream live and you can call in. So we're doing the best with what we got available. And I'm sheltering at home. And probably all your teachers are going to be doing that, by the way. They're not going to be on campus, I don't think. So maybe gross a little bit. If I take a look at this and just take these two quantities and put them in here, here's where I get. I have 1/2 the real part of V, and V is just this, right? So it's V0 plus e to the minus alpha Z e to the minus J beta Z. And then it's I conjugate. This is supposed to indicate conjugation. What happens when you conjugate something? You remember? If you had 10 at an angle of 30 degrees and you conjugated it, what would it be? 10 at an angle of minus 30 degrees, wouldn't it? Do y'all remember conjugation, the term conjugate? How many do? Nobody? Oh, one person. All right. In other words, if I have A equal to 10 at an angle of 30 degrees, A conjugate, and the symbol is just an asterisk right there, it would be 10 at an angle of minus 30 degrees. That's all conjugation does. So it's V times I conjugate. It means that's the voltage. When I go ahead and conjugate current, there's my current. Conjugation just changes the sign on J here. So it would be equal to V0 plus over Z0 plus times e to the minus gamma z, and it would be e to the j beta z. I'm about done. Do y'all see I just plugged those things in after conjugation, right? Can you all see what I did? I took I here and I conjugated, changed that sign, put it in, right? Now, I hope you can see it. Can you all see it?
Sure.
Right? What do you notice happening here? What is e to the minus j beta z times e to the j beta z? What's e to the minus 30 degrees, j 30 degrees times e to the plus j 30 degrees? E to the 0, isn't it? What is e to the 0 in one word? 1. So in other words, we get rid of these two things. Get rid of those. We're not quite done. Now I got to finish this thought. Just forgive me. I'm almost done, but forgive me, I want to finish this. Z0 actually has a magnitude and it has an angle. So it actually has an angle, e to the j theta of Z0. And the reason it has that angle is because if you have resistance and conductance that are non-zero, then you have loss. And then if you have loss, you'll have a complex value here. So this would be like 100 ohms, e to the j, maybe 30 degrees, something like that. With me, everyone? Now, I want you to look at this. When I did conjugation, I did not conjugate that. But if we conjugated it, I tell you what, I'll stop here and I'll finish this thought, pick it up next time right there, okay? But what's going to happen is, I'll just give you the answer because I'm over. P ab will have this form. It will be equal to 1/2 magnitude of V0 plus squared over magnitude of Z0 plus. And then it would be times e to the minus 2 alpha z, because there are 2 alpha z's there. And then it would be times the cosine of the angle associated with Z naught. And this would be the average power. And this is the power flowing down the line. Now, I'll cover that next time and do a little more on it. But I've got a question for everybody, and please be honest. Did you understand the way I delivered this lecture?
Yes, sir.
Is everybody okay with it?
I mean, I understand the process, but for the concepts, kind of confused. Like, I don't know where to come from.
Well, I really used circuits as much as I could. When I started the lecture, I was trying to make everything directly related to your circuits courses. When I talk about wires, inductance, capacitance, and resistance, and then build from there. That's what I try to do. I don't know if I did it as well as maybe Dave Irwin could do it, but I tried. And the other thing I want to tell you about, if you have any comments about how to make it better or worse or anything like that, let me know. I do not like using just PowerPoint or use PowerPoint because I think it numbs the mind of students. When I write like this and you have to write it down, you have to think about it and things pop in your mind. And don't be afraid to ask me a question. You know, this is a small class. The best single way to learn is direct interaction, and there are no dumb questions. There aren't. There's a lot of questions that aren't asked, and those would be considered the dumb ones because you don't answer things that you're curious about.
Okay.
Now, when I ask you questions, be honest with me. If you don't understand something, I'll never ridicule you or anything like that, but I'll try to, as best I can, explain it from a perspective that hopefully you'll understand. Now, how many people are not in Auburn? If you're not in Auburn, one, you're not in Auburn, 2, 3. So I got 2 people so far in Auburn I'm seeing, right? And then I got the rest are away. Let me just say this. Ben, you're in Auburn or not?
I'm in Auburn.
1, Tyler,
Yes, sir.
you're in Auburn. 2, Caleb,
No, sir.
Anthony,
No, sir.
Fowler.
I'm in Auburn for now. I'm gonna go home soon though.
All right, well, 2.5. Ying,
Yes, I'm in Auburn.
all right, that's 3.5. I mean, I don't know. Is it Singal Wang? Are
You can just call me Kyle if you want.
Kyle's trying to be easier.
Yeah, because that's hard. I understand. No, I'm
Are
not.
you in?
Yeah.
You're not in Auburn? All right.
No.
Now, if anybody has internet problems, let me know. Because I had one student that had a tornado, or I think it was some tornado damage to his area, and he was offline, and I had to do all sorts of stuff to make it work for him at the end of last semester. But if you have any internet connectivity issues, deal with me. What I'm going to do now is just, I mean, you guys are free to go. You probably have other classes, but Ben, could you upload that lecture and send me the link, and I will put it on OneNote. And also, I'm going to, on the OneNote page, what I would like you to do to give is to, I think I can give you access to this, is to have you put down your email address, your preferred email address, and that way Ben can contact everybody for this group me and stuff like this.
Okay. And also, I have a quick question.
Mhm.
Are we gonna do the actual like problems like for practicing during the lectures?
Yes, and the first lecture I can't, but
Yeah.
I have, there's the concepts I have to put out there. I'm going to assign homework every class period. I'll give you the solutions most cases. I'm going to let you work on it, and then any uncertainty will clear up. And I'll be happy to, I like working problems. My preferred way of delivery is this. I give you a reading assignment. All right, I go through some concepts in class, give you a reading assignment, try these problems. After you do the reading assignment, if you don't understand something about it, then in class, we'll spend time working it, because working problems is the way you really learn this stuff. It's not just having a professor talk about the virtues of, you know, the wave equation or something like that. It's always solving problems. That's where you work out the things you don't know.
And do I just drop our emails right here?
What I'm going to do is this. Everybody should be able to get on OneNote. Have you all been able to get on OneNote? There's a OneNote link I sent everybody, okay? OneNote is something I use. Dr. New uses it, Gofu New. He's in digital electronics. A lot of people use OneNote because it's very easy for me to put assignments up and not have to worry about Canvas's problems. And I can allow you access to it, so you can write your emails down there. You can, and for posting questions, I think GroupMe is best because you can directly interact with each other, or Facebook, one of the two. And all right, I'm going to close it down. But does anybody have any other comments or questions? We're running over. I know it. No. Any thoughts you have, just let me know about this course. And I appreciate you all being here. I'll try to figure out what happened to the rest of my class because they're not here. So we can just shut it down now. And Ben, when we get that link, send me an email or about it, and I'll send it to everybody. Okay.
All right.
You good here? If you have questions, this is my office hours right after the class, so ask away. You don't have to stay, but you can go. But if anybody has any further questions, go ahead.
Thank you.
Nothing else?
Well, we see the due dates for the assignments. Oh,
Yep.
it's always due on Tuesday or
It's due the
Thursday.
class period after the one I assign. I mean, like there'll be stuff due on Friday, or yeah, Friday, because we meet on Friday. But when I say due, I'm not going to collect it. Not this Friday. But I want you to do the assignment so we can discuss it if you have problems, okay?
Okay, but I thought it's part of grades.
The homework, not the collected homework will be, but this, I'm going to assign homework
Oh.
all the time.